Okay, this will be the lecture for Chapter 1, covering mostly units and vectors. So what we're going to cover today is introducing physics and talking about the fundamental quantities that we're most interested in, which is mass, length, time, and you could probably say temperature as well. And more importantly, about the units that we're going to be using to describe these. So I'm going to be introducing the SI system, or the metric system. I'll talk very briefly about significant figures. I'm not a huge sig fig person, so I'm not going to knock you if you don't use the correct number of significant figures, but I do have to introduce them briefly. More importantly, we're going to move into what a vector is and what a scalar is, and how to add vectors both graphically as well as through using components. I'll talk briefly about unit vectors, and then I'll talk about two ways that we can multiply vectors together that you'll be seeing in both Physics 241 as well as Physics 242. Now, before we dive too much into some of the math, let's just talk about, what is physics? What we're really trying to do with physics is we're trying to describe the natural world using the language of mathematics. Physics is largely experimental. For example, let's talk about gravity for a second. We know that things are going to fall at a rate of 9.8 meters per second squared. We didn't come out of the womb knowing that. We had to do experiments and then come up with a physical theory. It says, okay, we think that things are going to fall and accelerate at a rate of 9.8 meters per second squared. Once you have a theory, then you test it, you test it, you test it some more, you test it again, and once it's very well established, then we would call it a physical law or a principle. The most important thing that you're going to get out of this classroom is going to be able to think critically and solve problems. For example, in my previous life, I worked at NASA, and they didn't care that I could solve projectile motion problems, which you're going to be doing in a short chapter or two. But what they really cared about is that I could identify the problems and I could figure out a way how to solve it. Now, how do we go about that? First thing you want to do is identify everything that you know and everything that you want to know. Go ahead and just write all that down. You know distance, velocity, and you're looking for time. Then essentially kind of set it up, take a look through the notes, take a look at the book. Essentially what you're looking for is you're looking for equations that relate these things that you know to things that you don't know, that you want to know. After that, execute it. That's going to be largely math, algebra, and a little bit later on calculus. And lastly, evaluate it. Does it make sense? Did you get a speed that is larger than the speed of light? Does that make sense? No, it really does not make sense. So that's kind of a brief overview of how we go about solving problems in this class, which is again, very, very, very important. Now, for the physical quantities that we're going to be talking about in this class, largely in the first couple of chapters, we're going to be talking about length, we're going to be talking about distance, and we're not going to be talking about that in the more conventional feet, miles, everything like that. We're actually going to be using what we call the SI system, or the metric system. And what that means is everything that you do in this class should be done in terms of meters, not in feet, not in inches, not in kilometers, but in meters. The base unit for mass is not going to be the pound, as we have here in the English system. It's going to be the kilogram. Fortunately, for time, the SI unit is seconds and the English unit is seconds. When we hit the last couple of chapters, we'll be talking about temperature. Here we're used to how many degrees Fahrenheit it is. We'll be talking about it in the unit of kelvins. Now, you may be asking yourself, why, oh why, Dr. Rogers, why do we have to use the SI system? Well, first of all, every scientist in the world pretty much uses the SI system, whether we're talking about biology, chemistry, as well as physics. Another reason is, let's just take water, for example. If we were to look at 1 cubic centimeter of water, that's also going to be 1 gram of water. 1 liter of water is going to be 1,000 cubic centimeters, which is also going to equal to 1 kilogram. So it turns out the SI units tend to be related to each other, other units, by a factor of 10. Take a look at English units for a second. A gallon of water, you're talking about 8.33 pounds. A cubic inch of water, 0.036 pounds. So not so nice. Life is not so good. Now, one thing about the SI system is we tend to associate metric prefixes with values, and essentially all that lets us do is that lets us put a letter that might represent a number. For example, suppose I wanted to represent a large number of meters. Suppose I wanted to represent 1,000 meters. I would actually say I'm going to write that as the number 1, and then I have this K here it stands for kilo. And if you take a look at this table right here, that kilo represents a value or a multiplier of 10 to the third. So really what I'm writing is I'm writing 1 multiplied by 10 to the third meters. So a kilometer would be 1,000 meters. You tend to see this in your everyday life. We talk about how many terabytes we have. Essentially we would say this is going to be 80 times, let's see, tera, 10 to the 12th, 10 to the 12th bytes. We could kind of do the same with 20 microseconds. We'd say 20 times micro, go down here, micro is times 10 to the minus 6, times 10 to the minus 6 seconds. So a much more concise way of writing things. Kind of the common prefixes that you're going to see in this class is you're going to see giga, mega, kilo, I don't think you'll see deci, centi, milli, micro, and nano. So these are the ones you're going to know. Now let's talk a little bit about converting units. Suppose I have something and I say I've measured something as 8,000 meters. Let's go ahead and convert that to kilometers, and I want to do that explicitly showing the cancellation of units. So the way I would kind of do this is I would say, okay, well, I've got meters up here. I want to essentially divide by meters, and if I know that there's 1,000 meters in 1 kilometer, kind of what's written out right here, then I'm essentially multiplying by 1 in this little bracket here that I just highlighted. And these units of meters are going to cancel out with those units of meters, and I'm going to do the math, and I'm going to end up with 8 kilometers at the end of the day. Now, one thing about units is I care a lot about units. I take off points for units. Now, why do I care about this so much? Well, let's kind of think about it. An equation has got to be dimensionally consistent. What that means is suppose I'm adding 3 plus 2. Now that's great if I'm talking about 3 kilograms plus 2 kilograms. We can all do that in our head. That's going to be equal to 5 kilograms. But suppose I wanted to add 3 kilograms to 2 seconds. That makes absolutely no sense. So paying attention to units makes sure that we're adding apples to apples and oranges to oranges, and not apples plus oranges. So always, always, always pay attention to units, and more importantly, always convert to the SI. So convert to meters, convert to kilograms, and convert to seconds. If you do that up front, then you will not have any problems whatsoever. Now, just another little example on converting. I'm going to go ahead and convert 3 minutes to seconds. Essentially what I want to do is I want to take this minutes and I want to divide it by another minute, and I want to convert it to seconds. Essentially what I have here in the bracket, that's just like multiplying 3 minutes by 1, and we all know that in 1 minute there's going to be 60 seconds. So you go ahead and you do the math, and I'm going to explicitly cancel out my minutes, and what I'm left with is going to be 3 times 60 seconds, or 180 seconds. Now, just a brief genuflection in the direction of significant figures, or sig figs if you will. Again, I'm not going to knock you if you don't use the correct number of sig figs. You see that enough in your chemistry and biology classes, and that always just never really worked for me. One thing to keep in mind is you need to count how many non-zero numbers you have, and so you can say 1, 2, 3 sig figs right here, 1, 2 sig figs. Essentially, if you do some multiplication, you can never have more sig figs than the least amount. So if you take 11.3 multiply it by 6.8, you're left with 77 point something 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 something. You would say, okay, I can only carry 2 sig figs right here. But really, I'm not going to knock you if you keep a couple more. When you add or subtract, the answer can be no more accurate than the least accurate number used. So take a look at this one right here. This number is very, very, very accurate. This number here is not very accurate. When you go ahead and you add these guys together, so you're going to get 33.1. You're not going to get 33.100002. You would say, okay, I just get 33.1. A lot of times when we're evaluating our answers, it's a good idea to just kind of make a rough ballpark, back of the envelope, or order of magnitude estimate of a quantity, just to give you a feeling for whether you did something wrong in your algebra and got some crazy number. And just kind of a brief example of this, how much would you tip a waiter or waitress on a $22 meal? Well, let's just say you want to tip her 20%. Now you can whip out your calculator and do that, or you can say, well, I know that 10% is just like essentially dividing by 10, so I'm going to take this meal, I'm going to divide the cost by 10, and that's going to be 2.245. Alright, I want to tip her 20%, that's double 10%, so I probably want to tip her, about maybe $4.50. You're not going to tip the waitress $20, and you'd probably be called something really mean if you tipped her like 20 cents.